So this is a video about a little bit of the theory of absolute and conditional convergence. Um, and it's not incredibly necessary if you're just doing like a BC Calc version, but it's really cool stuff. So here's one theorem that we need to really confirm that it's true, that if a series converges absolutely, then it really does converge in the ordinary sense. So in other words, if when I strip off any possible minus signs, that converges, then the version with the minus signs converges. Putting in any pattern of pluses or minuses can't hurt you, is the claim. And that's not completely obvious because it means that you get, as I said in the other video, you get some sign cancellations, so the sizes of things are kind of smaller, but you introduce more wiggling. And one way that sequences can diverge is by wiggling. And so we do have to actually prove this. And what I want to do is actually I want to introduce. This is slightly different from the proof in the book. I think the proof in the book is not, in Stewart's book in particular, is not terribly well motivated, even though it's real quick. Typical textbook kind of thing. Let's look at, for example, the example I had before where it's reciprocal squares, and it's minus if it's the square of a prime, but plus if it's the square of a composite. Minus. Okay. Okay. So there's our series with the minus signs included, intentionally making it not alternating, so we couldn't use that kind of test. Okay. And so I'm going to say that we're going to create. So this has a sequence of partial sums. 1, 1 minus 1/4, etc. Okay. And what I'm going to do is I'm going to create two new series. I'm going to say the plus part is everything with a plus sign, and just zero out the minuses. And the minus terms are going to be they're going to be the minus ones, but I'm going to actually change them to plus because I want to be able to use theorems about positive term sequences. So it's going to be the negation of the minus terms. So that's plus 0, plus 0, plus 0. And the next one, it's going to have a 1/121, etc. So they're both positive term sequences. So anything we know about those guys is going to apply. And the key is that the sum of a sub n will be the sum of a sub n plus minus the sum of a sub n minus. Now, I got to be really careful. If both of these individual ones both converge, you can't do this kind of thing if these are divergent. Okay. So, but my claim is that if, let's see if I can have some room up here. My claim is that the sum of absolute value an converges. So the original guy is said to converge absolutely. That's exactly when both of these converge. So that's two things. I want to show that if these two converge, then the sum of the absolute values does. And if this sum of the absolute values does, then the individual, the plus part and the minus part converge. Those are both really easy statements. Because suppose that I do know that the sum of a sub n plus and the sum of a sub n minus do converge. Suppose somebody's proved that for me. Guess what? Kind of natural place to put it here is the sum of those absolute values is exactly what happens if I add these two guys together. Because I've stripped off all the minus signs, and if I put them back by adding, I'm going to get everything without minus signs. That's exactly the sum of the absolute values of the terms. And this is a very common thing. You take something apart into positive and negative pieces, putting them back in one way recreates exactly what you had with the signs as they were. Putting them back another way gives you something with the signs stripped out. Similar story with integration as well, if you prove various things about integration. Okay, so if these two guys converge, we have a theorem that says the sum of two convergent series converges, and that's this guy. Okay. If this guy converges, okay, this guy is everything with all the plus signs. Well, look at this. This is a sequence of positive terms, a series whose terms are positive, and they're less than or equal to the absolute values. Because this, whenever it's a plus, you have a non-zero thing, it's equal to the absolute values, and 0 is certainly less than 1/4. This is less than 1/9. So this is less than the sequence with all plus signs. This is also a sequence of a series with positive terms that compares to the absolute value. So just by the comparison test, really nice, easy version of the comparison test, says that if this guy converges, where I throw in everything with a plus sign, well then certainly if I throw in only some of them with pluses, or throw in some other ones with pluses, those are going to converge as well. So in a way, absolute convergence, maybe it's better, it's just a little less tidy. You might want to think of it as, if I separate out the pluses and minuses totally separately and add them up separately, they both converge. This prevents any kind of sign cancellations. And so it's a strong thing to say that if I sum up all the plus parts, it doesn't go off to infinity. And I sum up all the minus parts, it doesn't go off to infinity. And the cool thing is, if I know that, then I know two things. Okay, I know if they individually converge, then certainly it converges absolutely. That's what I was saying about this equivalence. But once again, this was the statement I really wanted to get to. If I know these individually converge without separating them out so they don't have a chance to cancel off with each other, then the sum of the original sequence I wanted to converge does converge. So this claim says that suppose somebody is verified it converges absolutely in this usual sense. They don't know about this trick about splitting into pluses and minuses. They say, I'm just going to put everything together with pluses, and I notice I have some tool that says it converges. Then we say, you know what, if you separated the pluses and minuses, they would individually converge as series with positive terms. And then if I put them back in with the signs, all I'm doing is I'm subtracting one series from another. And we know that the difference of two convergent series converges. So that's it. That's the proof. Stewart has in the book, he does a version that's kind of a similar idea, but it's very asymmetrical, using just this and the a sub n, and it's with a 2. I think it's kind of artificial. He also has a homework problem that is more like what I just did, but it's just a homework problem. Most people aren't going to do it. Okay, so here's one other thing about the theory. There's a really cool thing about conditional convergence. It's cool because in a lot of ways it's kind of bad. It's usually considered a kind of a pathology of conditional convergence. Conditional convergence you want to be suspicious of. It is a kind of convergence. If something converges conditionally, that means that, remember, this means that the sum a sub n does converge. But if we do throw out the minus signs, or if we did what we were just doing with separating out the pluses and the minuses as two separate ones, they don't converge. So I'll just remind us of that here. So this is more than we would say in the book. None of these converge in that case. Okay. So it means that the minus signs are necessary. Or let's say the alternate, or the combination of pluses and minuses is a more precise way to say it, are necessary. The sign cancellations are necessary for convergence, like the alternating harmonic series, for example. Okay, that means that these are very sensitive, and things that you would like to do, and things that you're able to do with absolutely convergent series, you can't do. So here's the two facts. One is that if sum of a sub n is absolutely convergent, not conditional, then there's a very cool thing you can do. Then I can rearrange the summation and do it in any order, and it'll still converge and get the same answer. And that's actually a really big deal. It might not seem like that, because you can usually, when you add a finite number of terms together, you can always do it in different orders, but it's actually a really big deal. So a rearrangement would be like, suppose I take 1, plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus 1/36 plus, and let's say I want to add it in just same terms but in a different order. Let's say I'm going to take 3 prime square terms before I take the next composite. And then I'm going to take 3 prime square terms before I take the next composite. What's the next composite? 36. And do it in that funky pattern. That's going to have the primes come way early, and the composites are going to come way later. I'm going to get everything eventually, but it's quite a completely different order. And I'm not just swapping 2 or 3 or a finite number. I'm really kind of infinitely reordering it. Because this guy converges absolutely, this guy will converge and will converge to the same thing. But that is not trivial. That's definitely not trivial to prove. And it absolutely depends, if you will, on absolute convergence. Because here's the other fact, fact number 2, is if I have a series that converges, so I'm not trying to do crazy things like manipulate divergent series, which gets you into craziness and contradictions real quick, but it only converges conditionally, then when I rearrange it, I'm very likely to get a different answer. And in fact, here's the really cool thing. There is a rearrangement of this guy, same terms but different order, that converges to any number I want. Let's say any desired number. Or I can make it diverge. I can make it diverge to plus infinity. I can make it diverge to minus infinity. I can make it diverge by wiggling. I can make it by wiggling in different patterns. I can do a lot of crazy stuff with this. So if you've got this, and let's say as written, let's say I proved it's convergent, and maybe I even know the actual answer, and that's S. And I say, okay, it's set in stone, then when I add these things up, it's S. Let's look at an example. Let's look at the alternating harmonic, for example, to make things simple. Ooh, that should be minus. Yeah. I say, okay, I've got this series, and when I add it up in this order, like here's the partial sums, 1, 1 minus a half, 1 minus a half plus a third, and do that sequence and take the limit of that sequence in that order, I notice I get this cool answer. It turns out to be pi over 4. Not sure if, no, I don't think I've mentioned that before, and we'll see why the heck is that true. We'll see soon why that's true. Don't count on saying, oh, well, what if I do it in some other order? What if I do this kind of trick where I'm going to take I'm going to take some of the primes, and then I'll throw in a composite, and I'll take a lot of primes, throw in a composite, and hey, I'm getting all the things. I'm not doubling, I'm not duplicating, I'm getting all the reciprocals, I'm not even changing the signs, the odds are still plus, the minuses are still even. I should get the same number, obviously, right? Well, no. In fact, depending on what order you put it in, you could get 17. You could get 93. You could get minus 100. You could get going off to minus infinity. Going off to plus infinity. So I don't think I'll make a video right at this moment of how to show that, just because this is getting long. But if I have time, I'll do that.